All right, well, I want to give you enough time to finish your presentation, so let's not wait too long. Yeah, let's get started, everybody. Thanks for coming once again to our webinar series. Today, it is my pleasure to introduce to you Maciej Chrabąszcz. Maciej is an ASAT researcher at NASK and also a PhD student at the Warsaw University of Technology. And in his research, he focuses on utilizing inner representations of models to detect and mitigate unsafe behavior. And today he's going to tell us about this paper that you see on the screen called Efficient LLM Moderation with Multi-Layer Latent Prototypes. Thank you, Maciej, for joining us. Please go ahead.
Yeah, so thank you. So as said, I'm a PhD student and also working as an AI researcher at NASK. And I'm going to talk about this efficient LLM moderation. To be honest, this is quite a long project, which is going for more than a year right now. If you go to archive, you will see 3 versions, and this were nearly 4 rewrites of the paper. So there is a lot of hidden knowledge that I'm going to try to share that is not also available in this paper, because I think I got some intuition which could be interesting, even though it's not in the paper, because maybe some reviewers did not find it interesting, so we just skip it for the next versions. So just to start, of course, I'm going to talk about the alignment challenge. So I'm focusing on utilizing inner representations because they are flexible, let's say. When we are doing these fine-tunings or alignments using RLHF or DPO, we have to fine-tune the model once again, and also then we do not have the assurance that our model would not forget the previous knowledge. So there could be a problem with catastrophic forgetting if we try to adapt the model to new threats. And also there's a lot of research showing that this alignment is quite superficial. I think the best example is this paper from iClear from last year from Maciej Chrabąszcz, where he showed that asking questions in past tense changed the behavior of the models quite drastically. Like they started to produce the recipes for the bombs or saying some hateful things, which they were not saying when asked questions in present tense. So I think this is the prime example, in my opinion, showing the superficiality of the current alignment methods. And also, we have to be aware of the evolving threats. Like when we were starting working with LLMs, we were saying that, oh, they can generate hate speech and so on and so forth. Now they get access to our inboxes, they can send mails on our behalf, try to I don't know, buy something on eBay and so on. And these threats are evolving from month to month. Like the OpenClaw incident, in my opinion, was a prime example of the evolving threats, which happened quite drastically. Like I think most of us were aware of the problems with AI agents, what they can do, but it's not so obviously seen by others which are not into this field, and OpenClaw was one of the prime examples of going all in on agents without knowing if it's going to be what the risks are when trying to apply this. So to have a method which try to mitigate this, we can try to do input versus output moderation. So input moderation is just a simple filtering. We can view it as a simple problem. So before passing the question to our model, we are just going to screen it to ensure that there is no hazard. Like there are some obvious questions which we know we do not want to answer. So sometimes it's just better to filter those out. First of all, we do not want to have any chances of our model producing something harmful. And second of all, it's a waste of compute when we find out that the input, which we know that this question is unsafe, calculating the output, especially by the large models, this could make a lot of compute, which does not have to be computed. So we can save quite a lot of computations. And also there is a thing of output moderation, sometimes also done with steering. So this is kind of reactive control. once again, we can just try to produce the output of the model, try to say, oh, is it harmful or not? But also we can try to influence the models with methods like activation addition or sparse autoencoders. We can try to influence the model to behave differently, to try to distort these harmful behaviors of the models. So I think I would say that I mostly focus on AI control on my research with inner activations. I'm not fond myself of using sparse autoencoders due to the problem with training proper sparse autoencoder. I do not have compute such as DeepMind has, so it's hard to create a proper sparse autoencoder. But there are many methods even someone with limited compute can use for these problems. And today I'm going to focus on input moderation mostly. I can talk about my results regarding output moderation, but I do not have this in this presentation because we just focused on this simplest task, which is the input moderation, we can say. And current moderation tools for the inputs mostly rely on guard models, like everyone is, I think, knows what Llama guard is and so on. So these models are, let's say, quite good. I think even Anthropic created their own guard model on top of Haiku model one time. So this is something that even the big labs do, and I'm certain everyone should be doing that. But there is a problem with high cost. Like if we want to launch an, let's say, 8B model in our business, but we also have to have another guard, which is also 8 billion parameters, then we are doubling the compute or even quadrupling the compute, taking into consideration the complexity of calculations. And also they are really hard to customize. Like if we have a Llama guard model, but let's say we're a business which does in a specific medical domain, then this model could not be as useful for us as we want to, and trying to customize it for our use case would be really hard. And also there are latent-based methods, which I'm going to also show and which we tested. They are highly efficient. I think the primary example which I'm going to focus on is just probing right now, because I think it's really interesting idea and it works most of the time. But they are efficient, they are flexible, but they are lower in performance than guard models. Even if we go on with size of the models which we're probing on, they can also fall short on the benchmarks, at least, of the models. So I think the main issue, there are some works which try to do multi-layer ones, but not many probes focused on even trying to utilize multiple layers. So that's what we try to do. So we wanted to have a method which is low in training cost, high in inference efficiency, it's highly flexible, and achieves performance really similar to guard models, or even outperform it. So this is what we try to do, and this is our idea. Like we wanted to utilize multiple layers, which I'm going to go more into details throughout this presentation. So the main idea during training. So first we have this first phase, which makes it really computationally efficient, because you only need to calculate hidden states of the model which you want to guard once. Like if you have a data set which you want to use for this classification, then you just have to calculate prototypes for each layer. Then there is this sparse aggregation which I'm going to get more into detail later. But in the end, after all of this computation, you have this inference. So when your model is running, you know which layers you want to use for your classification, which is done automatically by our method. Then you just need to pass the model through, pass the prompt for the model, get the hidden representations, and then you are able to say whether this input is safe or not. So first of all, we focused on prototype-based classification. A few of my colleagues which worked on this idea with me were from the continuous learning part. So they had this good intuition related to prototype-based classification. So we just focused on utilizing nearest mean classifier due to it having a really nice generalization properties. At least for it was tested in continuous learning tasks and some other tasks, and it's also highly data efficient. Like it does not need many samples to perform well or to lower the variance of our method. And also this method is, we can say, intuitive. Like we want to create a prototype, like what is an main example which looks like something that is unsafe, and we create the another one for the unsafe ones, and then we can just by calculating distance to those prototypes of safe and unsafe samples, we can say whether our input looks more like this safe example or this unsafe example. So of course, in the easiest case, you can use Euclidean distance for that. But if you get more into math of the higher density spaces, you will find a lot of work showing that using Euclidean in such high dimensional vectors, it's really inefficient. It does not take into consideration any geometry of the model. So to try to make it better, we decided to utilize Mahalanobis distance. So in this case, we are taking into consideration the covariance matrix of safe and unsafe samples. So the main advantage here is that we are able to take into account the variance of our data, the variance matrix of our data. So we will find the subspaces in which distance are more important. So obviously, if you would have two distributions and they would be propolar to each other, then going in this in one dimension could not be as discriminative as going in the other. So by using the Mahalanobis distance here, then we are able to just take this into account. And by utilizing the Mahalanobis distance, we can go into the probabilistic setting. So this is just a Gaussian discriminative analysis. So anyone doing more advanced statistics or even intro to machine learning should have known about this method. It's really simple, and this allows us to just calculate the probabilities of being assigned to one or the other class. So there is a high connection to this Gaussian discriminative analysis and using Mahalanobis distance. So this is just a way of calculating probabilities. And this also allows us to optimize the memory consumption, because let's say that because we want to use multiple layers. So if you would want to save, let's say, 32 covariance matrices of sizes 4096, this would be a lot to save. This would be like adding one feed forward, not one feed forward, but one small weight inside the model. So because we utilized shared covariance matrices, we could really lower the dimensionality that we need to perform this classification, this final classification. So this just allows us to lower this complexity. Also, we did some tests related to using shared covariance matrix. So having a single covariance matrix for both safe and unsafe classes, and having independent matrices. And we noticed that most of the time, maybe not most of the time, even always, it lowered the performance of the final model. So this could show us that these safe and unsafe manifolds have similar covariance matrices. Or the other possibility is that just calculating this covariance matrix, or even estimating it, to be honest, it's hard in this dimension, and just doing a shared covariance matrix allows you to do it better. So because I said that we want to use multiple layers, I have not said why we want to use multiple layers. So the safety presentations we noticed are distributed throughout the models. Like many papers show that just using the middle layer is one of the best ways of going forward, but we wanted to test it more throughoutly, and we got results from multiple data sets, multiple models. So on the left, you can see performance when using different layers of Mistral 7B model related to those 4 tasks. So here we have Aegis, ToxiChat, WildGuard test, and XS test. And we can see that there is no obvious single layer, which allows us to achieve a perfect performance. And on the right side, you can see the performance distribution dependent on the layer for 4 different models. So also here, we can see that maybe most models have the highest performance in the middle, but there is no golden rule, like always take the middle layer to achieve the best performance. And also, one time I tried to do an Oracle classification. So I took all the predictions from all these probes trained on all the layers, and then tried to estimate what is our upper bound when we would use all the layers. And so in this way, I just try to estimate what is the upper bound of the performance we can achieve when using multiple layers. And to do so, because I know the labels, I just found even if at least one layer has a good classification of this sample, and I have it written down right here, it achieved 95% F1 score. So compared to the base model right here, it's quite a drastic change in the performance. So this was our intuition that using multiple layers could be a good way of achieving a probe which generalizes better to out of distribution tasks or to novel unseen harmful samples. And also it would take the burden out of us to try to optimize this single best layer to have the performance for our model. So to do so, we wanted to do a simple idea. So because we want to minimize the memory footprint and calculations of our method, we wanted to do sparse aggregation of the predictions. So simply, we trained those prototypes or calculated prototypes and covariance matrices on each of the layers. This allows us to calculate the predictions of each of those probes. And later, we utilized L1 regionalization on top of those predictions to have a, let's say, meta model, which uses predictions of all those probes from the models, from all the probes trained inside the models. And this allowed us to simply aggregate the knowledge from these models. And also because we used L1 regularization, we are able to select the most important ones. So when you utilize L1 regularization, it drives most of the weights to 0 if they are independent. So that's what we wanted to achieve, to try to select as few layers as we can to have the best performance for our model. So the idea is simple. To summarize how our method works, first, we calculate the hidden states from the prompts. Then, by having labeled samples, we calculate means and covariance matrices for each layer. And on top of that, we train the sparse aggregator model, which allows us to perform these predictions with fewer than all the layers, minimizing the complexity of our solution. And also because L1 regularization or regularization most of the time leads to better generalization. So we also didn't want to use some noisy layers. This could also, most of the time, these were the earlier layers which were first dropped out, which is to be predicted. So now after this introduction of our method, I'm going to talk about the experimental setup which we used. So we used 4 model families: Llama, Mistral, Olmo, and Qwen-free models. And for our benchmarks, because we wanted to know the generalization of our method, and also because I noticed some problems with guard models that they sometimes have quite a high false positive rate. We also took some neutral benchmarks. This way to ensure that our method does not have an harmful impact on benign prompts. So we do not want to flag benign prompts at all. Like because most of the time when you are talking about predicting harmfulness in the prompts, most people just use specific harmfulness data set and they show false positive rate there. But in my opinion, this is not as close to the real world as it is, because most of the time in these data sets, even if the questions are benign or these prompts are benign in harmfulness data sets, they are really close to the edge or close to the boundary of being something harmful. Like they are really similar. They sometimes utilize some. These questions can be responded harmfully by the model. So also we just wanted to ensure that on these benchmarks where we know there is no harmfulness, this would not light up in our case. So of course we achieved state-of-the-art performance. We used the 2 different models, these Ayub and Abdelnaby. These are just single-layer probes which either utilize the logistic regression or some XG boost or random forest on top of that. So we can achieve that. We can see that going from single layer to multiple layers, especially on models such as Llama or Mistral, gives us quite a big advantage over those models. Like our average score over all these data sets outperforms any guard models outside of wildguard. So the wildguard, we can say that is top performance which we can achieve in this model size, because it was trained exactly on the data set we used for training. So we trained our probes here on wildguard mix, which is which has its flaws. Of course, there are some problems with this data set, which I'm going to talk about later. But it's really hard to achieve a perfect performance there compared to datasets such as HarmBench or OpenAI simple safety tests or simple safety tests. So this dataset is hard and it has some jailbreaks. So the most important part for us was that we achieved a much better performance independent of the model compared to single layer methods. And also we achieved better performance than guard models. And here again, this is the problem with flexibility. If you want to fine-tune those guard models to achieve a better performance on this data set, of course we can fine-tune them on that, but it will be quite expensive because we have to fine-tune the whole model compared to our method, which is capable of running on a single A100 with 40 gigabytes of VRAM. So this is really efficient. Yeah, so we outperformed the guard models, and the most important part from it for me is not that we outperformed them. Like the most important part for me is that we achieved performance really close or even better when using Olmo model on wild compared to wildguard, because this shows the advantage of efficiency. Like we can see that LlamaGuard achieves a poor performance on wildguard mix of 76 F1 score. So we have to fine tune it. But for our method, if we would find another data set in which our method would perform poorly, we can do this update like in 5 minutes or something like that. And we do not have to worry that our model will collapse or something like that. And also another really important thing, for most models, our method had a really good scalability with model size. There is problem with Mistral models, but we believe that this is due to these models being trained on different data, possibly, because of course we do not know, because the 7B model was trained on different data than the 12B model and than the 24B, because they were released in, I think, at least 1 year gap or half a year gap between each model at least. But on the Llama models, which were trained, I think, mostly on the same data, we cannot be sure, of course. We can achieve a perfect scalability, like going with the active parameter counts. Our method just increases in performance. So this is another thing that is highly important, because having a guard model which has only, let's say, 8 billion parameters to guard a model which has, let's say, 600 billion parameters, there is a really big gap. And taking into consideration the current developments, there is a high risk that this smaller guard model is just going to be fooled by the larger model. Like if a larger model knows how to has much more parameters, there's high chance that it has better knowledge or better capabilities, and then it can easily fool the smaller model. But when using the inner representations, we know that it scales with the model size, it scales with the model capabilities. So this is a big advantage of a guard models, which can which is a big advantage and can be really useful, in my opinion, in real use cases. And also, I talk a lot about this efficiency. So we calculated flops differences for Llama model. You can see exact calculations, theoretical calculations in our paper. And also we calculated how much more memory our method takes. So when you doing it on Llama 8B, our computational overhead was, as you can see, thousands of percentage, and memory needed per prototype or per layer was just 24 kilobytes. So it's a really scalable solution. If you wanted to use non-shared covariances, so independent covariance matrices for safe and unsafe, it jumps up to something like 25 megabytes per prototype. So it's a big jump in memory, but it's still handleable. So it's not that bad. But as I said, in our experiments, we achieved even better performance when using shared covariance matrix. So I talked a bit about data generalization. So we wanted to test how our method compared to training single layer probes performs when trained on different data sets, because the results on table 1 were just trained on wildcard mix. Here we use different training data sets and try to analyze how our method performs compared to the others on out of distribution tasks. And we noticed that our method achieved a clear advantage. Maybe not always it was better, but most of the time, which in my opinion is sufficient just to say that it's useful to use multiple layers, achieved a better generalization. This is for Olmo model, and this is the worst case scenario. So in the paper, we also have analyses for the 3 different families, and our method is a clear winner for every model, for every training data. So this is just the worst case which we achieved. So even if we trained our model on a toxic chat dataset, it was capable of generalizing to model harms. So this is a useful thing to know. Like when we are using the representations, so the better the representations, the better will be our generalization. So this is also a big plus when using methods which utilize the inner representations. And also, of course, because I said that this is data efficient, so what about data efficiency? So we tried to, or we just did ablation related to number of samples per class. So here 100 means that we had 100 safe samples and 100 unsafe samples. And we can achieve that. We can see that even just using 10 samples can achieve quite a satisfactory performance. The variance is really high, which is to be expected when we are estimating covariance matrices of size of 4096 with just 10 samples. This is highly unstable estimation. So, and it could be the case that it would be unstable and you would get nuns. So also that's why in all these scenarios we used shrinkage estimators of covariance matrices. But when we go to 100 samples per class, we can achieve that this variance gets really low, and going to just 1,000 samples, which I think is not that expensive to achieve if you, let's say, have a specific need for this guard model. Just having 1,000 samples allows you to, in my opinion, bring this variance near zero and also achieve a really good performance. It starts to plateau from around these 1,000 samples. So we also mostly focused on instruction or post-trained models. So we also wanted to test whether we can achieve such performance when using the pre-trained model. And what we noticed is that using just pre-trained model also allowed us to achieve a good score, which was, of course, much lower than the instruct model. This could be to the case that we extracted the last token representation, and in pre-trained models, this last token could be different tokens due to the having no chat template. But when we used instruction models, then we achieved better performance because the representation was always taken from the same model. I do not remember now the name of the article, but I'm certain that in last year there was this exact article which showed that when you want to extract representation from the models to be used for some kind of detection, it's useful to always extract from the exact same token, like not from the exact same token position, but just from the exact token. So this also just gives us intuition why it was the case. And what is also interesting is that because we trained on wildcard mix, we can notice that there is much bigger gap in performance when using pre-trained model instead of instruct models. So we can notice that training these probes or these multi-layer prototypes on instruct models achieved much better generalization to other tasks. And of course, because thinking models or reasoning models are something that is of big interest right now, we wanted to check if when we are using those models, if it's worth to allow the model to think, to reason about the prompt which it is given. Here, we did it only on Quen models, but on a few different sizes of this model. And also, we used only instruct models when they were available, and we allowed them to calculate the reasoning, the chain of thought, and then we extracted the representation to be used by our multi-layer perceptron, either from the last prompt token or from the end of thinking token generated by those models. And we noticed that in smaller models, it's even worse to use this end of thinking token. But when going on with the size, so increasing the size to 4B and so on, it gives you a small performance boost when you are using this end of thinking token. But this performance, in my opinion, is not as high as we would anticipate or as we would expect it to be. Like having this small gain of 0.5%, it's really not that useful, taking into consideration the amount of compute you have to use just to get to this end of thinking token. So if you want to boost your performance, I believe it's worth allowing the model to generate its reasoning trace and then extracting the representations. But I would not expect that it would be a really big gain for the final performance. And also, because we talked about this sparsity, so we tested how the performance looks when you are using different practice of layers. So to do that, we steered the regularization strength used by our meta model, this aggregator. And for all the models, we noticed that it's worth using more than one layer, but it's never worth using all layers. So this is also to be expected, because of course, as we know, every layer tries to encode some different things. So here it is just about finding the optimal solution for extracting those layers which have a strong connection to the safety features. And also because we were steering those regularization strength, we are able to try to see how this importance of the layers changes when we are changing the regularization strength. And this is something that we notice, that each model has different behavior. So in this previous plot, when I was giving you per layer performance, we noticed that of course some models has different best layers, but this analysis allows us to see how these layers are selected together. So this is a, that we can say, more complex analysis, which allows you to analyze which layers contemplate best each other. So on the left, we have Bistro model, and it was easily seen in this previous plot that the middle layers are the best. And here we can see, just by looking at this layer importance, that it's useful to use these middle layers in this model. But on the right, when we are going onto the ALMA model, we can see that, of course, these middle layers are still important, but we can notice that even this last layer starts getting more and more important the more flexibility or the lower the regularization strength of our method is. So just to sum up, as I have shown before, there is no golden rule which layer to select, and we believe that this spread of safety importance or the safety features is dependent on the architecture, on the training data. So we believe that there is no single golden rule of thumb. Like in the middle layers, we have the highest connection to the safety. This is not always the case. And also, because I was talking about steering, so we decided to try steering methods together with MLPM as a conditioning switch. So if you try to steer to increase the safety of your models with steering vectors, you will often find out that the steering disrupts the benign prompts. So this is something that we wanted to test out. There was this paper, this Lee et al. From 2025. It was also ICLR. I think it was Spotlight paper about conditioning, but they were utilizing specific triggers, which were calculated just as vectors, similar to representation engineering. They were extracting first principal component vector, which they were then using to calculate whether this prompt, which is input into the model, is safe or is not safe. And this can be viewed as using our method, but with Euclidean distance. So yeah, so just calculating this direction which they did, and using projection onto it as a thresholding is mathematically the same as using safe and unsafe prototypes and using Euclidean distance. And what we noticed is, of course, that this conditioning really increased the F1 score. Here, F1 score is just the harmonic mean between attack success rate and false refusal rate of the model. But what is, in my opinion, really interesting is that instead of adding the steering, just adding a simple refuse message was the best performant method together with our MLPM. So this was quite interesting for me because I thought that using such a method would drastically increase the false refusal rate, but it was not the case. The steering factors were much more disruptive on those benign prompts. And I also tried to really tune out those steering vectors to lower this false refusal rate while lowering lowering the answer. But it was really hard and tedious to do, in my opinion. And this could also be the case why these results are not that perfect, because I was unable to properly tune those steering vectors. Okay, so we also talked, I said that we utilized this GDA. So we also did some analysis of using GDA on a single layer compared to using logistic regression and other methods which can be used for probing. And we found out that most of the time, like here, 75% of the time, the GDA achieve highest performance. Which just gives us another proof or another evidence that this usage of prototype or distance-based methods is really robust. And the final ablations was because we changed from Euclidean to Mahalanobis, and we also changed from single to multi-layer. So we also tested what gives you the biggest performance boost. And the highest performance boost was given by going from Euclidean distance to Mahalanobis distance in terms of nearest mean classifier. But on top of that, adding this multi-layer also increased the score. It was dependent on the model. So I do not have a good intuition here why Olmo and Quen models have smaller boosts compared to Llama and Mistral ones. I believe that this could be the case that they were overtuned for this or for similar tasks, they were overtuned. So using just a single layer was enough to extract as much performance as you can from those models. And I also said that we extracted presentation from the last token, and we compared extracting the last token presentation versus mean representation. And unlike some papers that I've read, which show that using mean representation is better, we noticed that it's worse. And for some models, it's much worse to use mean representation, mean over tokens, of course, instead of using this last token representation. And also, we did some analysis. Where did this MLPM miss? So here you can see percentage of misclassification by all the four models, so ID 8 or 7P models. And we noticed that most of the time, this misclassification was when using these social stereotypes, sexual content, fraud, private information. And when we looked up those samples, we noticed that they were not so obvious to say whether this prompt is harmful or not. There were many samples which I believed were unharmful, or they could be they on their own are not harmful, but I believe that there is a way that model could respond to them harmfully. So this could be the case why we misclassify them. But it's worth noting that the violence, defamation, cyber attack, and causing material harm were the lowest ones. So I think this would be the most harmful ones. So for me, it was really interesting to see that the less obvious the harm is in the data, the lower is the performance. This is, of course, maybe to be expected. But for me, it was interesting to notice it that our model fails in similar samples when for me, it was not so obvious to say whether this is safe or unsafe. And the limitations of MLPM, in my opinion, the main limitation is the dependency on the LLM. So because we are using the inner representation, if they are poor, our method will be poor. So this is the biggest limitation, in my opinion. And also, I do not believe that using inner representations should be a single solution. I believe that this should just be a first or one of the lines of defense when we are trying to safeguard our whole solution. So it would not be able to take care of all the cases. And just to sum up, by using inner representations, we are capable of achieving or even outperforming heavy guard models. We achieve a high efficiency and data utilization or data efficiency. And our method is scalable with the model size, and it scales fluidly with the model size. So as we increase the model size, our performance increase was almost monotonically. So this is a really good way of good thing about these methods. Like as I said, with guard models, we have 80 model, and we want to guard the bigger model. To scale it up, we have to fine tune the bigger model. We cannot just simply use the same model as a way. So this just allows us for an easy scalability. And from my end, this is all. So here you have a QR code for our code. So you can use it just to get to my GitHub page. And if you have any questions, I will be glad to answer them.
Thank you very much, Maciej, for this super comprehensive presentation and a very interesting one. Please join me, everybody, in thanking Maciej, giving him a round of virtual applause. And yes, if you have any questions, please go ahead.
I have a question.
Yeah.
You mentioned that RLH have some problem with efficiency. How about different approaches to alignment phase, like constitutional AI or deliberative alignment? How they're fare in comparison to RLHF?
Yeah, so I didn't have much experience in those methods, but I believe that there are a good way forward of increasing the efficiency. But as I said, most alignment or most safety gains are through the alignment phase. And if your method is, if your model is not aligned properly in the post-training procedure, I believe that using this constitutional alignment and so on has some lower performance. So I believe it's good to connect them, but you always have to increase the alignment part or help the alignment part. And this is an important one and just a hard one to fix due to the computational problems. Of course, alignment is much less computationally expensive than doing the pre-training. At least as far as I know, I'm not certain if in bigger lab it's a bigger problem. But yeah, so as I said, I do not have much experience with those methods, but I believe they are a way forward. But I do not believe that we have a good way of, let's say, continually updating the models to have better safety. Yeah, I would sum it up this way.
Okay, thank you. I have another question. How the training data for the task of creating these prototypes is created, how it's labeled and so on?
Yes, so we just utilized dataset which was released at NeurIPS last year. It was wildcard mix dataset. So these are just prompts and responses which are labeled mostly by models, by LLM judges. But I think it was like 3 LLM judges. So of course this dataset is also not perfect, but I believe that due to the data efficiency of our method, you could create a high-quality data set with human annotators, which would lead to a much better performance or much better alignment with your way of thinking about harmfulness.
Thank you.
Yeah, I have a question on one of the slides towards the end of the presentation. And by the way, this was like very impressive. You mentioned like error analysis for different categories, and you hinted that you believe that the categories where there was more misclassifications were having the issue. Let's say that different laborers might have put different labels essentially for these like categories. And I was wondering if you have some measures of that. Like I would find like very interesting to compare the misclassification to human labelers' disagreements on the category.
Yeah, I would love to do that, but I do not have the money to do that because this data set, like I could spend like few hours to do so. I just didn't find the time for that. I just skimmed through the misclassification, and to be honest, it was really easy to find a sample which I, after reading it, like I was, is this really unsafe? Why was it labeled unsafe? Like I think one sample which was labeled as unsafe was a question, where does Captain America live? So I'm not certain why. Like I believe this is a copyright, the private information violation by their
We
measure.
don't
But
want to dox Captain America.
yeah, maybe not. Yeah, so I would love to do that, but I unfortunately was unable to do so.
Yeah, that's interesting. I was looking at a WildGuard Hugging Face page, and it seems that I think 80-something% of this data set is synthetic. So maybe there's like a case to run LLM like multiple times and then like gather their disagreements and get like another version of the data set. But just an idea.
Yeah, this is also in my opinion the problem with such data sets. Like there are not that many high quality data set available for the public right now. So of course, if I would be able to have much better higher data set higher in quality, I believe this method will be much better, because I believe now there is a lot of noise in this data. As you said, 80% of it was synthetically generated, so it's to be expected that there are a lot of errors there.
Okay, any other questions? Okay, I have a few on my own, but they're quite technical, so yeah, okay, I can try. So I have a question about this whole concept of like prototypes and also about the Mahalanobis distance. So first of all, let me just clarify. When you're computing the prototype, this is supposed to be some kind of a statistically average representation of a safe prompt, right? So am I correct that the prototype is not a single vector? It's not a single activation vector, but like a distribution of all the safe vectors?
Well, when we calculate the mean and covariance matrix, we can view those as two statistics which describe our distribution. But the prototype on its own is just a single point in its high-dimensional space.
Okay. So let me go to the Mahalanobis distance then, because from what I remember, Mahalanobis measures the distance between a point and a distribution, right?
Yeah.
So what is the point and what is the distribution that are being compared here?
Yeah, so here we are creating 2 points. So one point is the average representation of unsafe samples, and the other point is average representation of safe samples. And the distribution is just a Gaussian with this covariance matrix. So when we are passing your new prompt from there, you are essentially calculating the distance to the distribution of mean samples and of unsafe and safe samples.
Yeah, okay. So exactly. So a new prompt at test time, that's like a single point in the activation space, and you're measuring the distance between that point and the like safe distribution and the unsafe distribution.
Yeah, exactly.
Okay, cool. So then the next question is, I guess, you need to have some sort of a threshold for deciding whether it's closer to the safe distribution or the unsafe distribution, or are you just literally taking the minimum of these two, and that's your classification?
Yeah, so because we utilize this probabilistic, the Bayesian way of using Mahalanobis distance, we were capable of calculating probability of being in one and the other class. So we just used a simple threshold of 0.5. So yeah, but this could be tuned, I believe. We did not want to do any tuning, just to leave this method as is, but I believe there's a high probability that you could achieve better score when you properly tune this model. And also, this is one thing I did not mention. Like with our method, you can tune this threshold. So if you want to lower the false positive rate, you can just lower this or make this threshold of saying something is harmful higher, and then you can lower the false positive rate. So this is another thing which allows you for a steerability.
Yeah, exactly. Because that's literally what I was thinking about. That, for example, in AI control research, I think when they design those thresholds for when the AI monitor triggers, they usually optimize for, I believe, minimizing false positives because they're prioritizing cost as opposed to false negatives, which is quite concerning in my opinion. Because like they'd rather have fewer false positives than fewer false negatives. Just the other way around.
Yeah, I think what's most common way of calculating is just calculating false negative rate when you have false positive rate at something like 1%, something like that. So this is the most common case, but in the data set we use, most researchers just use this F1 score. But of course, this could be calculated the same way it is done in the AI control research. When, as you said, you have a specific false positive rate which you want to achieve, and then you are checking your performance on the toxic ones.
Mm-hmm. Okay, does anybody have any other questions? I have one more, but I feel like I should not hog the microphone. Okay, then apologies, but I'll allow myself one more. I'm very curious about this Mahalanobis distance, so because like I recently was working on a problem and I had where I had to quantify the difference between two distributions, right? So not a point in the distribution, but two distributions, and then there's this Wasserstein distance, I believe, W1, W2, and I was reading about some literature regarding optimal transport between two distributions, this sort of stuff. And yeah, your point about the difference between Euclidean distance and Mahalanobis distance was very intriguing. So towards the end of the presentation, you said that the biggest difference in terms of safety performance came from switching from Euclidean to Mahalanobis, right? Do you have some kind of an intuitive understanding of why that's the case?
Yeah, so my intuition from my mathematical background just says me that because this space is so big, using Euclidean distance is not the proper way of calculating the distance, because you have these 4,000 dimensions, and saying that going in dimension 100, one step to the right, then one step to the left, is the same as going in dimension 200. It's not the same, dependent on the distribution. So the performance gain is due to that you are capable of finding this, let's say, optimal subspaces or optimal dimensions where moving is more important or more discriminative compared to the others. So this is just adding another layer of complexity for your analysis. And yeah, I think that's just it, in my opinion.
I see. So like the point is that with Euclidean distance, you're essentially grading each dimension as equal, whereas with Mahalanobis, it kind of allows you to put a relative weighting, so to speak.
Exactly that.
I see. Okay, well, I need to learn more about how Mahalanobis distance works in 4,000 dimensions, I guess, to better understand this intuitively. Okay, yeah, last chance to ask questions. Okay. If there are no further questions, let's thank Maciej once again for his very thorough and interesting presentation and for sticking with us through the questions. Thank you very much, Maciej. It was very interesting. And before you all drop off, let me put the link to the next presentation in the chat, as always. So it's going to be on Thursday, 2nd of April by Jan Dubiński, who is, I believe, a co-author of yours on this paper. And I think Jan is going to tell us about jailbreaking VLMs, vision language models, so also a very interesting topic. Okay, so yes, don't forget to sign up. Thank you, Maciej, once again. It was great seeing all of you at our webinar series, and yeah, hopefully see you in 2 weeks. Thank you very much.
Yeah, thank you. If you have any further questions, feel free to catch me up on Slack. I will try to answer them if you have any. And if not, yeah, thank you once again and have a good evening.
Thanks, Maciej. Thanks, everybody. See you later.
Yeah.